What's going on? My name is Tosh Dalday. This is STG Labs. Welcome to class. Physics! What up, dudes? I'm going to be doing one last problem. Here's what we got. It's an inclined plane problem. It's angle theta. Now, this one's kind of a weird one. I'm going to do it kind of on a pulley, and I'm going to put a block here. We'll call this M1. We'll call this block M2. Oops. M2. We'll have the rope go over the pulley like that. Now here's the funky part. This will be my positive X direction, and this will also be my positive X direction. Again, the coordinate system's kind of bending around that pulley over there. What forces do I see? Well, this part gets a little bit funky. I've got the weight of the object on the first mass. I've got the weight of the second mass. I've got the tension pulling up this way. And I've got the tension pulling up this way. I also have the normal force that is going on between this thing in here. I don't like calling it capital N. I'm just going to call it F sub N. That would be the normal force acting between this object right here, or between the mass 1 and the actual inclined plane. And then what I'm going to do is, let's see. This part gets a little bit funky. I'm going to break this guy into its components. And you guys are saying, wait a second, W1 is in the vertical direction. Why would you break something that is not at an angle in the into its components? And my answer is this. It's because I actually slanted my coordinate system. Usually your coordinate system for this thing goes X in the horizontal, Y in the vertical. And then you break up all of your forces that you have in going into, either the horizontal component or the vertical component. The problem is I hate doing that. I mean, it's not hard, I just don't like doing that. If I could choose to, I'd rather only do it once than 3 times. But if you look at this thing, the tension is going in that direction, the force normal is going in that direction, the acceleration is going in that direction. That would be a whole lot of vectors to break apart. So what I would rather do is, if my coordinate system kind of looked like that, then what I would rather do is kind of turn my coordinate system like that, where this is the positive X direction and this is the positive Y direction, and then this guy is no longer in the like my positive Y direction. So in order to do that, I would break this up into its components, and that would make this theta. I think there's some justification that needs to be had here. This is kind of old school geometry. But if this were theta, then what is this angle right here? Yeah. And what is that angle right here? My answer is that's theta. Let me see, what's the best way to prove it to you? I think maybe the best thing I could do is I can take this drawing and kind of just move him back over there. So these lines are parallel right here. Alright, let's see. You can kind of think of this as, imagine, let's do this. I know I drew a bunch of lines, but I think that I can justify this to you. Imagine taking a cross right here, or this coordinate system, and then just taking it and shifting it up like this. So I'm grabbing this part and I'm moving it this way. That would take this bottom part and move it by the same amount. If I move this 30 degrees, that will move this thing 30 degrees. So this will be theta as well. That kind of justifies for me why I called that theta in there. I know it's a little weird. Okay. In this case, this would be Wx, this component right here, and this would be Wy. Let me draw it up a little bit bigger. Here's W, here's Wy, here's Wx, here's theta. Wx is actually W sine theta, and this Wy is actually W cosine theta. Now, that's going to be a lot different from how you're used to seeing it, because usually we give you theta being this angle over here. But since we gave you theta being this angle up over here, it kind of switches the sine and cosine a little bit. Because now this is the opposite side, and this is the adjacent side. I'm telling you this just so that you don't freak out when you see Wx equals W sine theta, because you're used to seeing it Wx equals W cosine theta. Or maybe Vx is equal to V cosine theta. Alright, so let's see, Wx is W sine theta, Wy is W cosine theta. I was going to write it in here, but it's a little bit small, so I'm just going to leave it. Why don't we just solve this out? Let's go sum of the forces in the x direction on mass number 1 is acceleration in the x direction. What forces do I see in the x direction? Well, I see a Wx, which is a W sine theta. And that's going in the negative, because it's going that way. I also see a tension, plus tension is equal to M1A. Now I'm going to go on the second object over here. So I'm going to do sum of the forces in the x direction is equal to mass 2 times acceleration. And, all right, I've got a t, which is pointing up. So that's negative t plus W2 is equal to M2A. By the way, I just put a little subscript 1 on that W just so I can remember what I'm doing here. All right, let's see. I want to solve for t, so I'm just going to make this W2 minus M2A equals t. Then I'm going to take that t and I'm going to plug him in here. So I have negative W1 sine theta plus W2 minus M2A equals M1A. I'm going to kick that guy over to that side. And so I'm left with negative W1 sine theta plus W2 equals M1 plus M2 times A. All right, let's see if I have some more room. I might be running out of it. I'm going to start working up here and let's see what we got. I'm going to pull out, actually W1 and W2, those are M1 times G. This is M2 times G. I'm simply going to pull out the G. So I have A equals M1 or M2G minus M1G sine theta. So it's M2 minus M1 sine theta times G. Did that pop out there? No, that's not enough room. All right, let's see. If it's all right with you, I'm going to start erasing some of this over here. I just needed more room, I'm sorry. A equals M2 minus M1 sine theta times gravity divided by M1 plus M2. Shoots, brah, up out.